Um, Welcome back, everyone. So today we are going to have Emanuela from University of Manitoba, and she's going to tell us about cohomology of line bundles over the incidence correspondence.
Okay. Thank you for inviting me. And yes, everything that I will say today is joint work with Annette Cohomology, Claudio Raico, and Ethan Reed. And V, through all this talk, is a vector space of dimension n. Over an algebraically closed field K. Okay, so I want to talk about flag varieties. And last week we already I have a talk on this. So a flag variety
Oh, we have to do it.
The idea is we want to study the cohomology of line bundles over flag varieties. And in the case of characteristic 0, we have that the cohomology is completely studied and like that from the Borel veil Butt theorem. While for characteristic, this is a mainly open problem. So today, I want to focus on a specific flag variety that is called the incidence correspondence. It's a partial flag variety. And it's the variety that parameterize the chains of subspace of the form. So we have the space dimension 1 and subspace dimension n minus 1. I can, I call X. And so let's denote with P the projective vector space associated to PV. Okay. And then I can write X is the couples PH, where P is a point inside the hyperplane H as contained in P product of P. Sorry, I said I call it P, so P. It will. Okay. So when n equals 3, then this is the full flag variety. While otherwise is a partial flag variety. Okay, so we want to study the cohomology of line bundles. So the first thing is like who are the line bundles over X, and every line bundles over X is of the form that is just the restriction of over X. Okay, so the goal is to study the cohomology of these line bundles. Like AB is in just integers. Okay, so first, let's see what is already known about these cohomology groups. So from first, for the case n equals 3, we do have formulas from the dimension and from the characters of this cohomology due to Dunking. 7, Gao Raiku. That we give a recursive formula for the characters. And recent Odorny gives also like a closed formula. What else we know? We know when exactly when these groups are 0. And this is by Gao Raiku. And the interesting case is when, and from this, I know that the interesting case, and I mean, the interesting case, is when I is equal n minus 1 or I n equal n minus 2. And what I mean with this, when n is equal I minus 1 and n equals 2, they can be an extra cohomology respect to the case of characteristic 0. So in these cases, there are like a cohomology group with some extra hypothesis here. Like one of these needs to be positive and one negative, for example, plus other hypotheses. But in this case, we know that like there can be extra groups. So I can just like look at these specific ones. Okay, and finally, in the same paper of Gao and Raiku, they reformulate this problem in terms of the cohomology of divided powers of the cotangent bundle. So let's explain a bit better this point. We have that, like, I call omega the cotangent bundle P, and R for me from through all this talk will be the shift of this. Okay, and D, so the D is the the cohomology for I equal 0 or 1 of over P of the divided power of R shifted by E is equal to I plus N minus 2 of X on the line bundle over the incident correspondence with E plus 1 minus D minus N plus 1. With tensor by this. So this is how they reformulate this problem of computing the cohomology of the line bundle of the incidence correspondence as computing this other cohomology. And like I was saying here, this is like for the case that we want to look at, for case for n minus 1 and n minus 2, where we do have this correspondence. And so I can restate the goal as study the character that I will denote by that by definition is the character. So of this cohomology. And I want to study this for I equal 1 and 0. And I can also assume that E is bigger than 0 and E is bigger or equal than minus 1. So the character, this is, I can define it as sum. That's it of the dimension of the graded piece. I'm not gonna write just, okay, D R E in the degree A times Z1 to the A1, the N. So the grading, this Zn grading is due to the action of the torus on my groups. And so the character is just the dimension in this specific multigrading times this monomial. So I encode all the dimension of the multigraded piece. Okay. So let's look into more background and how to explicitly write this cohomology group that we want to study. So okay. So at this point, we want to study this. This cohomology group from I equal 0, 1, D bigger or equal than 0, and E bigger or equal than minus 1. And so we have the exact sequence. And we obtain this sequence from the Eulero sequence. We shift and we apply the divided power functor with some work. You take this sequence here. And then from here, I can actually come to the cohomology, taking like the long exact sequence from the global section sequence. And so we have 0 of E The H0 applied to this is just the V tensor S. And you can think of these as polynomials on degree E or on the basis of V. The map, my map, the delta E D, the -1 V tensor E +1 V. And this goes to H1 of and there is not H1 there, so this goes to 0. Then I want to, this map here, knowing this map is enough to compute both H1 and H0 because this then will be the kern. And H1 is the cokern of this map. So calling this map 1 for later. Okay. The second reformulation that we can, so now it's already more explicit, but we can have a second reformulation of this using local cohomology. So, yes. So this one, I mean, it's you take the Eulero sequence, that is, because this is so you start by this, you're gonna shift it by E and apply the divided power function. There is some steps that I'm like hiding there, but that's like when you like you have to simplify something when you apply the divided, but that's how that comes from. That's the process. Any other questions? Okay, so the second reformulation is use local cohomology. The second one I apply like I take global section and the cohomology. So like this, the H0 of this, it will give me this, H0 give me that. And after I have H1 of this, but all the others are 0, so I stop there. Is it okay? Okay. So the second reformulation is local cohomology. So I defined the ring S. So let's say that X1 and Xn are a basis of V. And Y1, Ym is a basis of V dual. Okay. I can take the ring S as K, X1, Xn, and R, the ring S, Y1, Yn. So my ring R has these variables and this set of variables. And I think of that as this one in degree 1 and this one in degree -1. I define omega to be the form X1, Y1 plus Xn, Yn. Okay, so this, if you think geometrically, this is the form that it will define my incidence correspondence in the product here. But just to give an idea. But okay, so I define M to be the local cohomology, the N local cohomology with support in Y1 in the ideal Y1, Yn of R. And just to take that take care of that, the tensor product with the dual there, I will also tensor this with this. This will not change anything in like when I study the subject, but it will change in the when I study the character. I will have like the degrees will be like up one more. So that's why I'm doing this. And I consider the map M. Okay. So if I'm thinking so this is a big graded model. If I give degree 1 to the x's and degree -1 to the y's. And it turned out that this is exactly this.
Okay, question.
Yes.
So your bi-grading is, you're saying the x's have like degree 1, 0, and the y's have degree 0, -1?
Yes.
Okay.
So this is actually, you can. And moreover, if I want to look at this map in the specific degree, this map is the map that takes sorry, I usually write the E first just to not. So I'm increasing by 1 the x's, but I also increase it by 1 the y's, but the y's are degree -1. So this goes to E plus 1 D -1. This is exactly the same as the map delta ED. So this is a second reformulation because this is the same. Okay. So
to jump into my eye that these are really the same.
you can this. I mean, no, it should like it's not like straightforward like that, but it turns out that this is something like this. Where the sum of EIs are E and the sum of the I's are D. And you can prove that this is this, and also this thing is actually that. So if that's the intermediate step that is, no, it's like not like trivial on the note, but that's like the intermediate step that you can see. And the +1. Okay. Okay, so in this reformulation, we have that my cohomology is then the kern of this map here, if I equal to 0, and the co-kern of this map is I is equal to 1. Okay, and now we have like a third step that I want to do is because, okay, this is, I actually want to study this piece. I want to study, I have a ZN gradient here, and I want to study each multi-degree pieces. And so I can also put at the end grading on my M, just giving degree of xi equal the vector ai, and also the degree of yi minus the vector ai. So this will give me a ZN gradient on M. Okay, then you can show that this, the piece of multi-degree A1, AN is actually, and this is not like trivial to see, but like this is isomorphic to the monomial complete intersection A1 plus 1, AN plus 1. This NZ gradients turn out to be the right NZ gradient that we want, and is also compatible with this B gradient here. In particular, I will have that if I want to consider this map, ED from E plus 1, D minus 1, this is assuming that, and here I put an assumment that the sum of AIs is actually equal to the sum of A plus D. If this happens, then this is just the piece of degree E of this. Maybe not this parenthesis. 1 plus 1, and plus 1 in degree E. If this doesn't happen, this is 0. So this is the only case that like I will have this piece. Oh, sorry. I want the multi-graded piece. So like here I'm like I composing this ZN grading with the B grading that I had before. And I'm saying that like the piece, these two things are like actually compatible. And this piece multi-graded and also consider the grading is non-zero when the sum of AIs, where A is, I define like the vector A1, AN. When the sum of the AIs is equal to E plus D, then this is non-zero. And this corresponds exactly to the normal graded piece E of this monomial complete intersection. The multiplication it goes to the same thing of degree E plus 1, and V, using this isomorphism, translate actually to the multiplication times the sum of the variables. So this is basically my short reformulation that is only for 3. So what we have that this piece, this little piece here, for each A in Z to the N, I can write it as a kern and co-kern of actually this map that is a map between monomial complete intersections. So I will have that H I of E, the multigraded piece, multigraded degree A1 AN is equal to, but is the kern of the multiplication T1 plus Tn in degree E when I is 0, and is the co-kern in degree I plus 1 when I is 1. So the co-kern, oh, sorry, wrong parenthesis. I usually use the other parenthesis, but here. Okay, so, and in this case, which one is the co-kern? But the co-kern, I just take the DL generated by all of this and also of the sum of the variables. So this is K, T1, Tn over T1, A1 plus 1. T1, Tn in degree E plus 1 when I is 1. So all of this, let's recap 2 first, I wanted to see this cohomology and I can see it as a kern and co-kern of this map here. I can reformulate all of this using M, that is a local cohomology model. And finally, each multi-graded pieces, I can actually see a kern and co-kern of a map between monomial complete intersections. Okay, so from this follows that one, we have that age, the character in age I, let's do 1, D is equal to age 0, E plus 1, R, D minus 1. So there is a kind of asymmetry between age 1 and age 0 that is given by basically shifting the D and the E with a plus or minus, okay? But that means that we can assume A bigger or equal than D minus 1. Because if A is smaller than this, whatever I'm computing H1 or H0, I can use this formula and I go to the other one, but I will have now satisfied this property. So when I'm going to study my my characters, I can always assume E bigger or equal than D minus 1. The second thing that we have is that age, the character. So this is in general Laurent polynomial. But is also symmetric. So if I have the monomial x1, x2 square, I need also to have x1 square, x2. And last thing is that is the same as in characteristic 0 when D is strictly smaller than P. That's the characteristic of the field. And so, any questions? You can see, for example, the fact that it's symmetric from here, because like it's a monomial complete interaction, and it would be the same thing if I just like permutate A1, AN. And so, for example, from here, it follows that it's a symmetric polynomial. Okay, so our main result is that we give a recursive formula for all these characters. And we give a recursive formula. We use this as a base case, because when D is less than P, I can, is like in characteristic 0, and in characteristic 0, we know exactly how it is. So let's look at the formula that I pre-written here. But as I was saying, we are in characteristic P. We can assume E bigger or equal than D minus 1 because of that fact. And then we have this. So we can write the character as a sum of something involving smaller cases. Let's explain this formula. F to the P is the Frobenius endomorphism. This symbol is this sum. that he remembers maybe some truncation of a sure polynomial, but actually has much more terms because we are in characteristic to P. And hd to the P is the truncated symmetric polynomial. So is the sum of all the monomials of degree D with additional hypothesis that each of these are less than P. Okay, so this result extends the case n equal 3 that in Gao-Raiko. Also, for P, sorry, for D less than P squared proves a conjecture. No. So yeah, for when we assume that D is less than P, this is the proof of a conjecture contained in the paper of Gao-Raiko and van der Bogen. We, in general, do not have a closed formula for this, but we do have it in the case P equal to. So for characteristic P equal to, we have a closed formula, so not recursive. I'm now writing this on the blackboard, but these use the mean sum and sure polynomials. Okay, so the next step, I want to tell you, I don't want to do a proof of this, but I want to tell you which ingredients goes in this proof. Have any question up to here? Yes.
You're trying to determine the dimension of the kernel and co-kernel of this
Yes.
purple map.
Yes. So yeah, the character of that encodes all the dimension and codimension of that map. In characteristic 0, this is like clear which one it is, but in characteristic P is not. Any other question? What time is it? Sorry.
38.
Okay. Okay, the idea behind the proof that instead of study the map W between M and M, where M is defined as the local cohomology as above, we would like to study the map W to the R. So the powers of, sorry, omega, the powers of omega. And this seems more difficult, clearly, but we are going to do that in 2 variables. So the first ingredient of the proof, we assume for now n equal 2, okay? So V is a 2-dimensional vector space only for this step. And first thing is, okay, we want to study this. We know that W was like corresponding to that map there. What will be the shift that encode W to the R instead? Starting by the exact sequence that we have upstairs there, the first one, let's rewrite it from E equal to 1. Then we have the exact sequence delta D, because E is 1, to I'm just rewriting the sequence above for E equal 1.
So wait, do we want that to be
B
two? Is this E equals 1 or equals 0?
equals 0. Sorry, thank you. Oops. Okay. Okay, so the idea is, okay, let's imagine to compose this map R times. So if I do this R times, so I do this, and after I apply delta D minus 1, and after I apply delta D minus 2, then eventually I end up on this. By definition, we define the sheaf FRD to be the kernel of this map. It turns out that the sheaf defined in this way actually is a non-object because the dual of this sheaf is the so-called principal part. Or also called jet bundle. And I want to say this only to point out that in case of characteristic 0, this is actually well known and well studied. So we know how this thing splits in characteristic 0. And the question is, can we describe in characteristic P? So what we do is having a recursive description of the splitting type. We do this like always considering the action of the two-dimensional torus on this. So we want the equivalent splitting type. And using this, we give a recursive, again, description of the cohomology. So I want you to think about this as a description of the cohomology in the case the multiplication by W to the R for n equal 2. Okay, but this kind of just give you our description for n equal 2, how we get to bigger n from here. And this is the second ingredient of my proof, that is the Emanuela decomposition, the Emanuela representation ring, sorry. Okay, so, no. So, 2. And since our setting, we want to consider it graded. Representation ring. What, first of all, definition, what is this ring? So the Emanuela representation ring is the ring of isomorphic classes of finally generate graded AT models when the multiplication is given by induced by the tensor product. If I have two finally generate models, I can do a tensor product where T act on this diagonally. What I mean with this is so this will do some multiplication on my isomorphism classes of models. Now, each object here, it can be decomposed as a sum of irreducible. Which are the irreducible in this ring? So the irreducible in the composable. Are the form that shifted y minus j. And this is because we consider the graded case. And this is just the iso class of kt mod out by the ideal t to the c. So these are all the irreducible. And the big question here is how to compute the multiplication. This is not in characteristic 0, because in characteristic 0, this, when ck is equal 0, we can compute this, and this is just equal to the sum cj minus j from j equal 0 to I minus 1, and cj is a plus b minus 2j minus 1. So it's a pretty easy formula in characteristic 0. In characteristic, this question is open in characteristic P. Note that if you know the multiplication in between two things, since we are in a ring, I can know the multiplication between n things. It's associative, I just do it recursively. And maybe you ask, okay, what does this has to do with what we have on the blackboard? And the answer is, we want to study this multiplication with that, right? And if I take a monomial intersection, T1, A1 plus 1, Tn, A1 plus 1. The plus 1 is just to keep the notation consistent. But this, I can think of this is basically, it represents the object A1 plus 1 times An plus 1 in this category, where T is taken to be just the sum of the variables. So in this ring, this element, the monomial complete intersection, does the multiplication of this. And if I know how these decompose under the action of T, then I clearly know everything about this map. Okay. So these are the two main things in the proof. And I will not give you the proof, but I will explain how these things are connected. So we proved, first of all, the cohomology. Oh, thank you. Of FRD completely determined the product. And this is how we link these two things. So knowing the cohomology, we'll know everything about the product. We know only we have the recursive description of cohomology. So we don't have a full description by hand, but since we have a recursive description, we can use this to prove, we cannot have the full rule for the product, but we can prove some results property. I am in a ring. I know something about the product of shooting. I can actually translate it as some results on the product of n things. C1, Cn. And from this, then we use this to have the recursive description of okay, any questions?
I have to keep staring at the whole map, and this is kind of the prototypical example of a individuality algebra with a left shift element.
In characteristic 0, and that's exactly the application, but not the characteristic P.
So you're not allowed to vary this linear form?
No, I'm taking exactly that. And in any case, in characteristic P, not always that the left shift works. And that's actually the application that, how much time? 0 minutes? Ooh, then never mind. But I'm just saying that like, that's the point. And if I had time, I wanted to see an application, and the application for characteristic 2, when I have a full description, I can classify which monomial competing section have the weak left shift property in characteristic P. Because exactly like, that's exactly what you say, in characteristic 0, this is that. In characteristic P, that not necessarily works, and using the characteristic shooting, we can describe exactly when we have the weak left shifts and when not. Okay, then I stop here then.